Okay, so in this lecture, we will talk about superposition theorem. So what does it mean to superpose something? So to superpose something actually means to put something on top of another and adding up their effects. So for example, you have seen waves superposing on one another. For example, if you have two waves at the same place, same time, out of phase of each other, they destructively interfere, and if you have them in same phase, they are in constructive interference, and you have seen them in physics before. So what you are doing is adding up two waves, and their total effect is given by their added up quantity, right? So we can do similar types of things in circuit as well, although not as complicated as that. For example, say I have a circuit, so I have 5 volt here, 2 ohm here, 3 ohm here, 4 ohm here, and 7 volt here. And yeah, that's it. I guess we can see another example later. So we have to figure out what's this current. Okay, so the question is, how do you figure out the current? Now there are multiple ways. You can do nodal analysis, or you can do source transformation and stuff like that. But here we are trying to explore another technique called superposition theorem, right? So the crucial point to understand here is that any current this circuit has, so maybe this current or the voltage here or anything else basically, comes from just these two voltage sources, right? These two voltage sources are the ones who are supplying the currents or voltages, and you get the total current. So what happens is that if you actually just separate out the component, you are getting just the part coming from the 5 volt voltage source and just the part coming from the 7 volt voltage source, and add them up, you will get the total current. Okay, so what I am trying to say is the current I is equals to I 5 volt plus I 7 volt, right? I guess that makes sense. So the total current is added up, are superposed of the two components, so the two sources. And if in fact if we had like 3 sources, maybe another 3 ampere current source here, I don't know, maybe something like this, maybe we have a current source like that, like 3 ampere current source, then we would have a third component like 3 ampere. Okay, so you add up each of the components separately, each of the sources, the voltages and currents each of the sources are supplying, and you add them up. Okay, that's how you get the total current, the total effect. So you are superposing all the effects from the sources. All right. So okay, so we understand that, but how do we exactly figure out how much voltage or how much current the 5 volt voltage source is supplying, or the 7 volt voltage source is supplying? Okay, let me erase that 3 ampere part. Okay, so how do we figure out just the part from 5 volt voltage source? Okay, so for that we have to do something like this. Let me copy the whole thing. You paste it here, and let me paste it another time here. Okay, so I have pasted the same exact thing twice. Let me create a separation line between them. Okay, so to figure out just the contribution coming from 5 volt, all you have to do is turn the components coming from all other sources to 0. So what you do is turn all the other sources to 0. Okay, so here in the left circuit, I want to calculate just the power coming from 5-volt voltage source. Okay, so what I do is I turn the values of all other sources to 0. So I turn their contribution to 0, or as we like to call them, we kill other sources. We just keep the 5-volt voltage source alive and kill other voltage source and current sources. All other sources are killed. Okay, so I turn this into 0 volts. So the contribution from 7-volt voltage source is gone. Okay, so now you only have the contribution from 5 volts. So it's not actually accurate to write I here. You should write I 5 volt, because in the left circuit you are only getting the current from the 5-volt voltage source. And on the right circuit, I want to do the exact same thing. I want to keep this circuit alive, this voltage source alive, and kill every other sources. So here we only have one source, so that's not a big deal. So we turn this into 0 volt. Okay, so and then of course the current here will be just the current from 7 volt. Okay, so now we do the usual nodal analysis or something else to figure out this current. Okay, so you might be asking, how is this useful? Well, it's not always useful, but it has some benefits. For example, now you have for example, now you have okay, so now you have this, and the thing is, if you remember from the equivalent circuit video, this 0-volt voltage source is just equivalent to a short piece of wire, right? Okay, just a piece of wire. So basically, if I draw the box like this, I don't think that's necessary. So the 0-volt voltage source is just a piece of wire now. It's equivalent to a short circuit current. So what's the advantage here? Well, first of all, you have one voltage source left, one voltage source reduced. So you have number of elements have reduced, and also you have just 2 nodes right now. Okay, and this whole node is a ground node. Okay, so your computation might become a bit easier. Okay, and if you do the calculation, you will get I5 is equals to 0.77 amperes. Okay, that's the left side. That's just the component from I5 volt. And now we have to do the same thing again for 7-volt voltage source. Okay, so let's do that. Copy and paste. Okay, so again, here we have this box. Here we have this box, and the voltage source inside the 0-volt voltage source is equivalent to just a piece of wire. If you remember, it is equivalent to short circuit connection. And let me draw the box off so that it doesn't distract us from the main point. And now if you do solve the same thing again, and again we have here the whole thing is ground, you have one node here, another here, and you do the calculations, you will see that the current, after the calculation you'll find the current source, 0.7 current source. Sorry, I meant to say the current component from the 7-volt voltage source is 0.538 or let's just write 54 ampere. Okay, so that's the the contribution coming from just the 7-volt voltage source. But remember, we are here to find the total current I. Okay, so here the actual current I will be I 5 volt plus I 7 volt. So you add them up, 0.77 plus 0.54 ampere, and if you add them up you will get 1.31 amperes. Okay, so that's our answer. Now you can do the same thing with just one circuit, just solving this whole circuit with nodal analysis or something else, and you'll find the same exact current. So for superposition, what we do is separate out the contributions. So we have to kind of copy the same circuit 2 or 3 times the number of sources, of course, and separate out just the contribution from one components each, and then add them up. Okay, so this is the main procedure for doing superposition theorem, and it comes in handy for some scenarios, not all scenarios, and that's the same for actually any technique here. So not all techniques will be equally useful to you. Okay, but when it's useful, you can use it. Okay, and in one scenario you are kind of bound to use superposition theorem, and there is no other way. So that's why it's handy to know. Okay, so I want to first kind of show you the procedures stepwise. So first step, what you do is step 1. First step, what you do is create. Okay, so keep one independent source alive and kill all the others. Okay, so there's one important thing I did not mention here. Okay, so independent source. So superposition theorem is the only one that kind of distinguishes between independent source and dependent source. So if you remember that if we have a voltage source or a current source, not necessarily 10 volt, anything actually, or a current source, maybe 5 ampere, if you have the exact value of that current source or voltage source, then we call them independent. So they are not dependent on others. So their values are not independent. Their values are not dependent. Okay, dependent on others. Okay, they are independent sources. This is an independent voltage source, and this is an independent current source. Okay, and then we have dependent voltage source and current source. So if you remember, we drew them like this in one example. So if you have like the value is not exactly something written with just one constant value, we like to write it like something maybe 3Vx. So maybe in somewhere in the circuit you have a voltage called Vx, and whatever that voltage is, 3 times the voltage will be the value of this voltage source. So we draw them with a rectangle. Okay, and same with current sources. I said before that it doesn't matter really, but we use it to kind of differentiate between them. And again, maybe this also has a value of 3Vx, so maybe some like the voltage there Vx, and the 3 times the voltage in SI unit, the current will go from here. So maybe you have a resistor here with Vx, so maybe the Vx's value is I don't know, maybe 5 volt. Then the current here is 3 times 5, 15 ampere. Okay, but it's not written exactly, and we don't know the value of Vx either until we have solved the whole circuit. Okay, so that's the difference between them. So these are called dependent circuits, dependent voltage sources. So what you do is you don't kind of don't consider them. So what we are going to deal with is just the independent sources. Okay, so we don't touch the dependent sources. We don't even touch them. Okay, they are sources, but we don't touch them. So we only touch independent sources. We only touch independent sources like we did here. We kill, we just keep one alive and kill the others, and then work out from there. Okay, so step 1 is to keep one independent source alive and kill all the others. And one thing to keep in mind, if you have a dependent source in the circuit, just leave it as it is. Okay, like you leave resistors alone, just like that. So leave the dependent sources alone. Okay, and then step 2 is simply just using some circuit analysis, like nodal analysis or something like that. Maybe you do nodal analysis or source transformation or other techniques, to solve the current or voltage component of that one source that was alive, right? That's what we did. So we kept these 5-volt voltage sources alive on the left circuit, and we calculated just the 5-volt current component from there. Okay, and then this is the step 2, and then step 3 is you do the exact same thing for all other sources, all other independent sources. So kind of what you do is repeat the whole thing. Repeat for all other independent sources. And step 4, well, you just add up all their effects together. So add them all up. So the source transformation technique basically does an equivalent circuit of a voltage source and resistance in series, or a current source and parallels in series. Okay, so it transforms from voltage source in series to current source in parallel. And superposition theorem, what it does, it separates out the problem into multiple circuits and lets you add up all the results together. Okay, so first we separate them and then we add them up again. That's what superposition theorem is. So I would like to show another example just to clear out the confusions. But this video is long enough, so let me show you on another separate video.